Right. So now I'm recording. So before we cover what I need for us to cover today, are there any questions regarding what we've covered up to so far? So any questions regarding um, what is this relative velocity or resulting velocity?
I do have a question, but now I can't remember now which one.
Is it on the textbook?
No, it's in one of your videos, actually.
Oh, all right. So one of the questions in my videos. Did you write it down, perhaps?
Yes,
Or maybe
that's
you
my
can tell
thing
us.
now, but
Maybe you can tell us if it's pertaining to relative velocity or resulting velocity.
I know I have a think it's VA is equal to, or VY is equal to 70 kilometers.
Mm,
Oh, I can't remember now that one.
let's
Can I ask? Maybe
let's check the problems on Moodle. Maybe it's gonna be
okay.
one. No, this one.
Excuse me, sir. Do you know if the issue on Moodle has been sorted yet? Because I still can't log in there.
The Moodle issue I'm sorting out myself now. So probably when I was trying to sort it out, or when I was sorting it out, you weren't part of that conversation, I guess. I registered a few students myself on Wednesday evening. Were you not
No,
part of
I'm
the
aware of that. I was part of that conversation. I sent you a private message, and then you said admin was still gonna register me
Oh,
on Moodle.
so you are one of the students whose student numbers I couldn't find on our LMS.
Okay.
No, I'm asking if you wanted them.
Yes, yes, I am. Yes, I am.
Okay. Yeah, then I guess I'm still waiting.
Okay. Thank you very much. Then.
Um okay, I can check here. Yeah, I'm still waiting. Right. The reason why I started registering students on my own is because I think we only have like one Moodle administrator, and she's responsible for essentially everyone. So it can take a while before she responds. And even if she does respond, it could take a while for her to actually solve the problem.
The videos that is on Moodle, are they different from the ones that's on your YouTube channel, or can we just go on the YouTube channel so long?
YouTube channel, same. I
Okay. Okay. No,
I
that's fine.
I only upload my videos.
Okay. No, that's perfect. Then I'll just watch your YouTube videos again.
All right, it's wonderful. So in the meantime, just remind me as well when we say get to a different topic, because sometimes I can forget that not all of you are registered on Moodle. So just remind me if I do not send videos or links to the videos on our WhatsApp group. Nah?
Okay,
Will do so. Thank you.
we'll do so.
Activity solutions. Okay, let's check here. Okay, relative velocity. What was one of the velocities there?
It it was saying actually, I think VAY was going north and and the other one was going northwest. but it had a 60 degrees angle.
60 degrees.
Northwest.
Let me see. It was one of my videos.
This is the very first video.
If it's the very first video, I think it's a problem.
Yes, I think so.
It's a problem on the textbook. But why isn't it up? Oh, this is the resulting. This is pertaining relative velocity, right?
Yes, correct.
Is it this one?
You have 100. Yes. My question on this one, it's concerning the angle.
Mm-hmm.
You can explain. Can you explain this section that you did here? Because I was under the impression that you're gonna use 60 degrees, but instead you use 30. I need a clarity on that. Yes.
Okay. All right. So let's read the 7. The car A moving or is moving due north at 70 kilometers per hour, and car B is moving 60 degrees west of north. All right. So this has to do with direction. Right. Look
Yes.
at how the direction is put here for car B. Right. They said car B is moving 60 degrees west of north. Right. So when the direction, right, when the format of direction has been given to you like this, right, where they first mention the angle, right, just
Yes.
like with this one, they mention the angle first and they say west of north, right? What you should do here is the last direction, right? So you have two directions, you have west and you have north. In this format, the first direction they mentioned is west of, the second one is north, right? So to better understand why I used 30 degrees here, you need to understand where this angle is referenced from, right? You need to understand where this angle is referenced from. And the way you can know where this angle is referenced from, right? If the format is like this one, then you take the second direction, you place it in front of the angle. So by that, I mean, so the second direction is north. So you're gonna have north first. So when I say you place it in front of the angle, right, it's gonna be north, then the angle is 60 degrees, then you have west. Right, so this is the actual direction, or this is a better format, right, for a direction. Why? Because it gives context as to where this angle is a reference from.
Okay.
Right, and this angle is reference from the first direction here, that direction being north. Right, so if the reason why I use this format for directions is because I know with this format, the first direction tells you where the angle is referenced from, and then the second direction, right, essentially tells you in which quadrant your vector is. Right, because if you say north, the vector could be in the first quadrant or the second quadrant. So in order to tell if the vector is in the first or second quadrant, if the first direction is north, is by looking at the second direction. Right, so if this is north 60 degrees west, means that it is in the second quadrant. Right, but what is most important here in terms of angles, right, is you have to know where this angle is referenced from. Hence, when the direction format has been given like this, you must change it to this format, because this format will essentially give you the context of where the angle is referenced from. And the angle is referenced from north. Now, north is on the y-axis. So if the angle is referenced from north, it means the angle is referenced from the y-axis.
Okay.
Right. Now, when using the method of components, I prefer referencing my angles from the x-axis. Right. That is why here I used 30 degrees.
Can you come again on that one?
So I'm saying I prefer when I'm going to use the method of components. So with relative velocity, there's two methods that you can use to get what you're looking for. You can either use the method of components or you can use the vector diagram. The method of components, right, makes use of what is this conditions of equilibrium. Hence, we calculate the component of the resultant in the x direction, right, and then the component of the resultant in the y direction, and then use Pythagoras to get the velocity we're looking for. Right. So because this method uses components, I prefer referencing my angles from the x-axis so that my components will be in terms of cos. I mean, the horizontal component will be in terms of cos, and the y component will be in terms of sine. Right. The only time the horizontal component is in terms of cos is if this angle is a reference from the x-axis. And the only time the y component is in terms of sine is if this angle is a reference from the x-axis. All right, so once the angle you are using is a reference from the y-axis, then these two change. All right, for instance, for the horizontal component, you would then use sine, and for the vertical component, you would then use cos, which can be confusing to you guys. All right, so to make sure that all your horizontal components are in terms of cos, I always reference the angle that is from the x-axis. Are we clear? You're not getting it. Hello?
Okay. I thought we were gonna use this. We're gonna use VBY is equal to 100 sine 60, not sine 30.
VBY.
Yeah, in both actually components. I thought we were gonna use the angle 60 that was given on the statement, not sine 30.
So what I'm saying is you could do that. But if you do that,
Okay.
then your VBY will be 100 cos 60. And your
Okay,
VBX
fine.
will be negative 100 sine 60.
I hear you. Okay.
You could use that. As long as you know how to use it, that's fine. All right.
Okay.
So hence I said the reason why if the angle is that's given is reference from the y-axis, I then use the angle that is, or I calculate the angle that is reference from the x-axis, is because you guys tend to confuse this here, which trig ratio to use in the components. So you would actually find students that are using the angle 60 degrees, but they, in the horizontal component, they make use of sine here. I mean, they make use of cos instead of sine. Because
Okay.
there's this misconception that horizontal components are always in terms of cos and vertical components are always in terms of sine, which is wrong.
Which is okay.
Yes.
Okay. Okay. Clear as crystal.
All right. So if you are able to resolve, right, a vector using an angle reference from whichever set of axes. That's fine with me. As long as you are able to do it, you understand it, then you should come right anyway. Are we clear?
Yes, yes.
All right. Did that make sense to everyone else? Because it seems I'm still talking to one person here.
Yes, sir. It does make sense.
One person who was looking forward to this session.
Sorry,
Hey.
sir. Can
Uh-huh.
I want to ask something?
Mhm.
I want to ask something about the science when we come to the science of when we say VA minus VB. Why is that, sir? Why are we not saying VA plus VB? Why are we minusing? I just want to understand that one.
All right. So let me just say first of all that this video I did a long time ago. I think it was the first time I took over the subject at Wingfield campus. Nah. So when I started,
Yes, sir.
I essentially was teaching students all the methods. In fact, not all, the ones I had used at that time. Right. By that I mean, so with relative velocity, you get relative velocity of objects that are on parallel planes. Right. So meaning that objects that are moving along the same plane, right? Be it the x-axis or the y-axis. When looking at objects that are moving on parallel planes, right? The way we express relative velocity is, say you have object A and you have object B, both of which are moving along the x-axis. So they are on parallel planes, right? Maybe this one is going in that direction. In fact, let's say both are going in the same direction. Both are headed east, right? And the question is, calculate the velocity of A relative to B. So in which case, that means that A in that scenario is the object and B is the frame of reference. So essentially what you're looking for is VAB. Now for objects on parallel planes, how we express that mathematically is we would say VA minus VB, right? So for objects on parallel planes, calculating the velocity of A relative to B means you are calculating the velocity of A minus the velocity of object B, right? That is what it means mathematically. So this here is from this concept. Right. So as you can see here,
Yes.
you have VAB, right? You have VAB, which means mathematically you have to subtract the two. Right. So this method, right, is from this concept. The concept we use when the objects are on parallel planes. Right. I no longer use this though. As much as it is correct, I don't use it anymore because of the question you are asking. Right.
Okay.
So when we do this, what we are doing is we are applying conditions of equilibrium. And conditions of equilibrium, right? Even this sign here, it means the sum of. So I found it hard to explain, right, why I'm saying the sum of Vx or of VAB in the x direction, and yet I subtract here. So then I came up with a better method where you applied the conditions of equilibrium the way you are supposed to. So calculating the sum of, as in you would say, sum of VAX plus VAB, I mean VBX. But now,
Okay.
when you draw the vectors on the Cartesian plane, right, you draw them differently, right? So when using this method or when using this approach, when you draw the vectors on the Cartesian plane, you draw them exactly as they've been given on the statement, right? For instance, they said car A is moving north, hence VAY is north, right? And then B, right, car B, they said is moving north, 60 degrees west, right? So if you look at the vectors, right, we drew both the vectors in the direction that has been given from the statement, right? And that is why we use this approach. But when you use the approach I teach students now, what you do is, so if you are going to be applying conditions of equilibrium, the way we should apply them, or the way that you would expect us to apply them, right? This has to change a bit, right? So that's your Cartesian plane. So how this changes is you first identify, right, based on the question, which of the two is the object, which one is the frame of reference, right? So here for A, the object is A, B is the frame of reference, right? So with applying conditions of equilibrium correctly, right, what you do is you draw the vector that represents the object in the same direction as the one you've been given, right? Meaningly, so A is the object. So we are going to represent A here in the same direction that is given in the statement. And in the statement, they said car A is moving north. So you draw the vector headed north as per what you are given, right? So the object, right, you draw in the same direction as the direction you've been given in the statement, but the frame of reference you draw in a direction that is opposite what you've been given, right? Now the given direction is north 60 degrees west. That's of car B, right? Remember for A, car B is the frame of reference, right? So the frame of reference you have to draw on the Cartesian plane in a direction opposite the one you've been given. So opposite of north is south. This remains the same. Opposite of west is east, right? Meaning this vector would be in the fourth quadrant, right? So it will be somewhere here. Right here, remember this angle is reference from south. South is along the y-axis. So meaning this will be somewhere there. And this angle is 60 degrees, meaning that this here is 30 degrees. And then of course you'd resolve it into its components. Right, so this would be VBX, this would be VBY, right? And then because this is the method of components, right, the fact that the velocity of car A is parallel with the y-axis, right, we are going to call it the velocity of A in the y direction, right, because this method is for the method of components. And then when it comes to applying conditions of equilibrium, Now you can apply conditions of equilibrium the way you are used to. So sum of V X AB. So now this will be VA X plus VB X. So this is what you are used to. So in order to use this, how you draw the frame of reference on the Cartesian plane must be in a direction that is opposite the one you are given. Am I making sense here?
Yes.
Yes, sir.
So both
Quick
methods
question.
are correct.
Quick question, sir. Sorry to interrupt you now. That VAX, do we have to put it there if there is no VAX, or can we just put in that VBX?
So let me put it like this. No? I do it like this for context. Nah. Once you understand what you are doing, right? Once you understand what you are doing, then you can. What is the question?
That VAX that you wrote down there now,
Yeah,
there is now no value for that VAX, is there?
there is no value for it because
It's zero.
VA, yeah, it's zero because VA
So
is
we
parallel to the y-axis.
So the
Yes,
question is, do I have to add
you
that
don't have to
VAX?
do it. No,
Okay, thank you.
right? Even I do it for context. But when doing the actual substitution, this will be equal to zero. So my response to you is, once you know what you are doing, no, you do not have to. Because remember, this is about showing that you know what you are, that you understand the topic, right? But as someone who's marking the topic, I don't necessarily need you to show me this here. The fact that, in fact, the fact that you understand that this is equal to zero, hence you don't need you don't even need to show it. It shows that you understand what you are doing, which is fine with me. All right. So this here is just for context for you guys. Just in case we had VAX, you'd have to substitute it here. Are we clear?
Yes, sir.
Yes, sir.
Yes, sir. Thank you.
Right. Any more questions? That's why let's just quickly go to Moodle. You guys have went through the activities I uploaded on Moodle, right? Where's this thing? There it is. All right. Have you tried these activities, these exercises? Hmm? Okay, I guess that's a no. Did you see this?
Yes, we have.
Hello?
Yes, sir.
Yes, we have.
You did see this?
Yes, sir.
Right. Now, if you look at my the methods I used here, I used both the method of components and the parallelogram. So you guys are familiar with both, right? But with the parallelogram, I'm going to show you a much simpler approach for the vector diagram. Right? You don't necessarily have to draw a parallelogram.
Okay.
Right? I'll show you a much simpler approach as far as the vector diagram. So here's this thing. So the vector diagram or parallelogram method. Right? I'll show you a much easier approach. Right? With this approach, right? As long as you are familiar with the cosine rule and sine rule, and you are familiar with what is this? With angles. That's not quite the word I'm looking for. Right, but if your trig is on point, right, you should be fine with the approach I'm going to show you just now. Right, but my point here is, if you look at the method of components, right, this is the approach I used, where I draw the object on the Cartesian plane in the same direction as the one that's been given, and I draw the frame of reference in a direction opposite the one I've been given. Right. So make sure to have a look at this. I'm going to send you more solutions. So the solutions I'm going to send you now, I'll only be using one method. That's the vector diagram. The vector diagram is a much easier approach. Right? Because there, what you have to think about really is how the angles relate to each other. But sometimes you don't even have to think about that. Right? But there are cases where you have to think about how the angles relate, so you can use the correct angle. Right? This will make sense when we do a problem. Right? Are there any more questions before we look at the vector diagram?
Hello, sir.
Uh-huh.
I don't know if I'll be going too far back, if we already covered this, but just wanted some clarification with here in the textbook, right?
Mm-hmm.
Question 4C.
Question 4C.
Activity 1.1, question 4C.
Activity 1.1.
Don't know if that's too far back or not, but yeah, if you can just say how one does that one.
Activity 1.1.
Yeah, it's on textbook, page 10. I think you just,
Number
by
40.
that mineshaft 4C, yeah.
Yes, the time taken for the cars
Yes.
to reach each other. Regarding the time taken,
Yes.
So with relative velocity, no,
Mm.
whether they say calculate the velocity of A relative to B or the velocity of B relative to A, the
Yes.
magnitude that you get will be the same.
Mm.
The direction might be different, but the magnitude is always the same. All right. So that is to say that the resulting or the resultant velocity is always the same. All right. So which brings me to how you calculate the time taken. All right. As far as how you calculate the time taken, you use the resultant velocity. So by resultant velocity, for instance, for A here, they said calculate the velocity of A relative to B. And then for B, they said calculate the velocity of B relative to A. When you calculate both of those, they will give you the same magnitude, right? So you take that magnitude. All right? Take that magnitude and you take it as your resultant velocity.
Yes.
So VAB is equal to VBA, which is equal to resultant velocity.
It's equals to negative velocity B relative to A.
So hence I'm saying only the magnitude. Don't worry about the direction.
Yeah.
So look at the magnitude of this one and the magnitude of this one. The directions are different, but their magnitudes are the same. So I'm saying
Yes.
here, the magnitude of this one is equal to the magnitude of this one, and we regard both as the resultant velocity. So when you have to calculate time, all right, you use this formula, S over T.
Okay.
All right, the S is the distance between the two objects.
Yes.
Yeah. So use VR, which is the magnitude of this, or the magnitude of this, which is the same. And then the S
Yes.
will be the distance between the two cars, the initial distance between the two cars. And then all you do is solve for time.
Okay. When you say S, right? Don't you mean like because you're saying S is equals to distance, right?
Yes.
Do you mean S should be equal to displacement?
So the reason why I
Because
say
velocity.
it could be distance, it could be displacement. Right.
Okay.
It should be displacement, but they sometimes say distance.
Or because whenever we have velocity, we immediately have displacement and not distance.
Yeah.
Yeah. Okay.
That
And
is
what's
correct.
the sign
So,
for what's the sign for velocity though, sir? Excuse
sign-
me. What's the sign for um the sign for displacement? Yeah. What's
the
the
sign
sign for that? Yes.
So
Because
here,
distance is S, displacement is what?
or distance is displacement. So how we normally do it is, for distance you would have S. For displacement, you put an arrow. So both are S, but the right way of doing it
Okay,
is
sir.
having an arrow, right, to show that this is distance with direction. So meaning displacement. But
Okay, no, I
for
see, sir.
for engineering science, it doesn't matter much, because
Okay.
your examiners do not contextualize things. Right? You find yourself looking at velocity. Next thing, they say you have distance.
Okay. Yes,
Hence,
yeah, I see.
yeah. Hence, I don't really like differentiate so much between distance and displacement.
Oh, sir, I see, sir. Yeah.
Yeah. So that is how you calculate your time. Just manipulate this equation, which is
Okay.
from.
Mm.
Remember, we have this triangle. So you have V, you have S, you have T. So when you're looking for T, you use S over V.
Mm.
Do you see
No,
what
I
I'm saying?
remember that triangle, sir.
Yeah.
Okay, that's my question, sir. Thank you.
All right, cool. Mm. This is relative velocity. Okay. Any more questions on relative velocity? Hello? No more questions?
No, sir. We continue.
All right. So I'm just going to show you this approach on the vector diagram. Right. So here, you say the fighter plane Q flies at 250 kilometers per hour east, while the velocity of fighter plane P is 210 kilometers per hour west, 53 south. Determine the velocity of fighter plane P relative to Q, right? Now with relative velocity, first thing you need to do is identify, right, of the object you've been given, which one you are going to take as the object, and which one you are going to take as the frame of reference. Yeah. So here, based on the question, they said determine the velocity of P. So the first letter is P, meaning that P is the object relative to Q. So Q is the frame of reference. So we are looking for VPQ, right? Meaning that P is the object and Q is the frame of reference, right? Why is that important to determine? It is important to determine for when we represent the vectors of P and Q on the Cartesian plane, right? So VP, right, is given to us as 210 kilometers. That's the magnitude. The direction is west 53 degrees south, right? West 53 degrees south. Remember what this means, right? This means that this angle is reference from west, and west is on the x-axis, meaning that this angle is reference from the x-axis, right? And where is P headed? Headed south, meaning that this here gives you essentially the quadrant that P is landing on. Then you have VQ. VQ is 250 kilometers per hour, right? Now for this question in particular, right, because Q, we've established that Q is our frame of reference, right? When drawing Q on the vector diagram, on the vector diagram or on the Cartesian plane, we have to draw Q in a direction that is opposite the one we've been given. Remember I said that the velocity of the object you draw on the Cartesian plane in a direction that is the same as the one you've been given. But the frame of reference you draw on the Cartesian plane in a direction that is opposite the one you've been given. All right. So because Q for this case is our frame of reference, then we have to draw Q on the Cartesian plane in a direction opposite the one you've been given. Opposite of east is west. So this is west. Now you draw the vectors on the Cartesian plane. All right, that's your Cartesian plane. Now we are going to draw the vectors on the Cartesian plane, starting with, now this part you need to follow. All right, this is the most important part. Let's make this, okay, let's make this green. This is what we are looking for. Let's make this, let's make it magenta. Make this one blue. All right, so magenta. Right, so VP being our object, right, is headed west 53 degrees south. So it's in the third quadrant. So this is somewhere here. That's somewhere here. Right, somewhere there. This is going in that direction. All right, that is VP. Right. From the x-axis to VP is 53 degrees. All right, how do we know that? Based on this direction. All right, remember that the first direction represents where this angle is referenced from. So because this VP is referenced from the x-axis, or the direction thereof is, or the angle thereof is referenced from the x-axis, It means from the x-axis to the vector VP is 53 degrees. All right, so just bear that in mind. Right, now, the next vector you're going to draw, which is VQ. Right, you draw the next vector from where the first vector ended. So your first vector started here and it ended at that point. So now you're going to connect VQ, right? You want to start drawing VQ from this point, right? In fact, the right way of doing it is by placing a small Cartesian plane, right, at the end of this vector, your first vector. So you draw a Cartesian plane, and then on that Cartesian plane, you then draw VQ. Now for this case, VQ is parallel with the x-axis, so it becomes easy in that sense. All right, so VQ is from here going west. Right. Now take note of the direction of the two vectors. Right, the two vectors follow a head to tail direction. Right, they follow each other. Right, they are following a head to tail direction. Now regarding the resultant, all you do to get the resultant is you connect the two vectors with a line. So you draw a line connecting the two vectors. Right, this line connects the two vectors, and the line that connects the two vectors represents the resultant. So this VPQ that you're looking for is this one. The resultant of the two vectors, or the resultant in a vector diagram, represents the velocity, right, that you're looking for. So in this case, we're looking for the velocity of P relative to Q. This here being the resultant of this vector diagram means that this represents V P relative to Q. The direction of which, all right, very important, that the two vectors, or the vectors of the two objects that you've been given, they follow a head to tail direction, but the direction of the resultant, right, the direction of the resultant opposes head to tail, meaning that it will go in that direction. All right. Remember, head to tail would be that. Right. Now, if the resultant, take note of this, if the resultant is following a head to tail direction, what that means is that the vector sum of the vectors is equal to 0. Right. So the resultant following a head to tail direction like the two vectors means that your objects are not moving. Right? And clearly that is not the case. The two objects are moving. Right? Hence, the conditions of equilibrium here are not fulfilled, as in the resultant is not equal to 0. So because the resultant is not equal to 0, then the resultant cannot follow a head to tail direction. That is why you have to draw it in a direction that opposes head to tail. Are we clear?
Yeah. Clear.
Yes, yes.
Right. So the two vectors follow a head-to-tail direction. Then you draw a line that connects the two vectors. That line represents the resultant, right? Which is what you're looking for. And then as far as direction, you just draw, you show a direction that opposes a head-to-tail direction. This here will give you an idea as to the direction of VPQ. Right? At this point, you now know that VPQ is in this quadrant. Any questions?
Can you please read the question for me again? I want to see something.
question.
Yes, please. Oh,
The question or the statement?
yes, please.
The question or the statement?
Yes, please.
The question or the statement, or both?
The question.
So the question is, determine the velocity of fighter plane P relative to Q.
Okay, and the statement, I want to say something.
A fighter plane Q flies at 250 kilometers per hour east, while the velocity of fighter plane P, or you got what you're looking for?
Yes. Okay. Thank you. Yeah.
Any more questions? All right. For relative velocity and resultant velocity or resulting velocity, this is the best approach. If I was you, I would familiarize myself with this approach because, right, in the exam or in your assessments, we do have a tendency of asking you guys specifically to use the vector diagram. So if you get a question, be it on relative velocity or resulting velocity, if part of the instruction in the question is to use the vector diagram, you have to use the vector diagram approach. If you use the method of components, even if you get a correct answer, it will be incorrect because you went against the instruction. Right? We never ask you to use the method of components, but there are cases where we ask students to use the vector diagram. Right? The vector diagram is very important, people. Right? You will see that when you get to N6. When you do mechanotechnics N6. Right? If I'll be the one tutoring you, we will start here on the vector diagram. Right? There is a module there called kinematics. Right? And it requires a bit of this knowledge, or it requires that you are at least comfortable with what we cover in N4. Right? That is why I only teach the vector diagram. I no longer necessarily teach the method of components. Any questions before we proceed? Can we proceed?
Sir, what was vector? Sir, what was vector diagram? We followed up with the cosine rule or the
Sorry?
sine rule? Or does vector diagram be solved using the method of sine rule or cos rule?
Yes.
Yeah.
Right. If you notice, it is a vector diagram, but we don't necessarily use the scale. That is why we make use of cosine rule and the sine rule. Right. So meaningly, this doesn't have to be like accurate. Right? In fact, this is for context for you guys. Right? It helps for context. If you're doing engineering, right, it really helps to draw. If you're dealing with vectors, right, it really helps if you draw the vectors on the Cartesian plane. It gives you context. Meaningly, even at this point, we haven't even started calculating, but you already expect that the answer you're going to get as far as direction of the resultant, right, must correspond with what you have on the Cartesian plane, which is you are waiting or you are expecting to get a direction that will be west, whatever angle you are going to get, south.
Okay.
Unless you calculate your angle from the y-axis, then it will be south angle west. Either way though, you expect your vector to be in the third quadrant, which can serve as a guide when you are calculating. Are we clear?
Yes, sir.
Yes, sir.
Okay. So let us continue. Right. So
Please,
what you've done, sorry?
please ask something here. Because I see, okay, right, you're saying that for protector, it's not necessary to use a protector
Yes,
in these vectors.
it's
Because
not necessary.
sometimes using a protector, you get the accurate answers. Like
Yes.
the one you get when you're using the trig function like sine and 10 and cos, yeah.
Yeah, you don't have to use a protractor because, like I said, we are not drawing the vector diagram to scale.
Okay.
No, copy that noted, sir.
Yeah. Right. That is why we don't necessarily call it a graphical method. We stick to saying it is a vector diagram method because we don't draw it to scale. Right? We make use of cosine and sine rule. Does that answer your question? Mnumzane?
Hello, sir.
Does it?
I'm answered, which means there's no need for this instrumental like rulers and stuff like that for this.
Nah, no need. No need. This you can draw either on the answer sheet or you can draw it on the question paper even. It's just for context.
Okay, right. And then which means when they specify that use components, and then which means I'm have to use components. But if they say vector, and then I have to use vector. But if they didn't specify, which means I can use the vector, and then I get the right answers.
Yes.
I'm comfortable with vectors actually.
Okay.
Yeah.
It's better if you're comfortable with vectors. Hence, I'm saying everyone must strive to be comfortable with this method. Right. Right. Now, after having drawn your vectors, right, we know that this one is 250 kilometers per hour. This one is 210 kilometers per hour. Right. Now let's work out our angles. Right, so let's work out our angles. The only angle we have at the moment is this one. So from here to there. So the angle from here to VP, which is 53 All right, 53 degrees. All right. Hello.
Correct, sir.
All right, so the only angle we have here is this one, which is 53 degrees. All right, so we need to work out one of these angles, either this one or this one or this one. All right, so let's call this A, B, C. This could be small a, small c, small b. All right, now we have to work out either angle C or angle A or angle B.
Okay.
All right, so which one can we work out here? Just
Now
think
we can
about
use
it.
By angle C, sir.
Angle
Angle.
E.
Yeah.
E.
Angle B.
I was saying by angle C, it's definitely a complementary angle.
Okay, so to save time, this is the angle. Angle A. All right. Angle A is co-interior. So this angle and this angle are co-interior. Are you guys familiar?
So can someone please turn off the mic?
All right. I think we're fine. All right. The angle we are going to work out is this one, angle A. All right. Angle A is co-interior with that one. All right. So if this is 53 degrees from here to there, right? This plus this angle should give us 180 degrees. Do you guys agree?
100%.
Yes, sir.
Agree.
Right. So calculate the 180 degrees because this is the one we're looking for. So say 180 minus the 53.
127.
127.
So it means here we have 127. That's that angle. Right. And then our vector diagram is complete. Right. Now, when it comes to which rule you use, right, it's going to be based on the angle or the angles you have on your vector diagram. Right. As things stand, this is the angle we have. Right. Then the angle we have is between two known vectors. Right. Meaning that we are able to take this as an included angle. Right. So essentially meaning an included angle will be the angle that is between two known vectors. So if the angle you have, is between two known vectors, so let's say here if given angle is an included angle. So by included angle in this context, we mean that the angle is between two known vectors. So if If given angle is an included angle, then use cosine rule. Right. As far as sine rule, with sine rule, you just need to have at least two angles and two sides that correspond to those angles, and you're good to go. Right. But for the cosine rule specifically, you can only use it if the angle you're going to use is between two known vectors. All right. So because the angle 127 degrees is between two known vectors, it means we have an included angle. Hence, we are going to use the cosine rule. So using the cosine rule, remember we are looking for VQP, and VQP here is side A. All right. So this will be A squared is equal to B squared plus C squared minus 2 BC times cos A. All right. The side you are looking for, so we're looking for side A, corresponds with the angle that you have, which is angle A. So we're looking for side A, hence our angle is angle A. All right. So this will be A squared is equal to side B is the 210 squared plus side C, which is the 250 squared minus 2 into BC, 210. C is 250 times cos A. A is 127. All right. Now let's see what A squared is equal to. So A squared is 210 squared plus 250 squared minus 2 into 210 into 250 cos 127. So I'm getting here 169 790,5774. Right. And then because we're looking for A and not A squared, right, you then use the square roots on both sides. Hence, A will be equal to square root of what we got here at the top. So the square root of this. Right, and the square root of that, square root of answer is 412. 412,057 kilometers per hour. All right, so again, the same thing here.
Yes, sir.
Yes.
So let me just rewrite this. So we are getting 412,057. Right, so now we have the magnitude. Right, remember A, right, side A is equal to the resultant VQP. So essentially we do have VQP now, right? But in calculating the velocity, you also have to stipulate its direction, right? So now we have to get this angle, right? We can call it theta. We need to get that angle, right? The angle is referenced from the x-axis, so meaning that our direction would be a reference from west. Right, now how do we calculate that angle? Right, now if you look at that angle, it alternates with this one, right? With B. So essentially, if you get B, you will essentially have that angle. Do you see what I'm talking about here? Right. This angle alternates with that one. This line is parallel with that one, meaning that these angles are alternating. Do you see this?
Yes, sir.
Yes, sir.
Right. So if we calculate the angle B, we'll inadvertently have the theta that we're looking for. So we calculate angle B using the sine rule. Right, so we say sine B divided by side B is equal to the angle we have, so sine A divided by side A. Right? And then now you manipulate this, making angle B the subject of the formula. Right? So angle B will be equal to arcsine of B right, so arcsine of side B times sine A divided by side A. Right. So this is equal to arcsine of this. So now you substitute. Right. Now we substitute. So substituting side B is equal to 210. So this here is 210. Sine A is 127. Side A is the 412,057. What do you get here? What is arcsine of 210 sine 127 over 412,057? So I'm getting here 24,017 degrees. Right, that's angle B. Right, and then as noted, angle B alternates with the angle theta that we're looking for. So now you can say, therefore, VR is equal to, its magnitude is 412,057 kilometers per hour. Its direction, the angle theta is referenced from the x-axis, and the x-axis are due west. This would be west, 24,017 degrees south. Any questions? No questions? Hello.
No questions, sir.
None from you, sir.
No question.
Right. We can end the session here today. Now, what I would like for you guys to do is to attempt the problems on relative velocity using the vector diagram method. Right. And then when you get to the resulting velocity, I want you to again attempt resulting velocity using the vector diagram method. Now, tomorrow morning, I'm going to record a couple of videos, right, on resulting velocity using the vector diagram. All right. So once I've uploaded those, I'll send you the links in the WhatsApp group. All right. I'll also be uploading the links on our Moodle page. All right. Have you guys started watching the videos on resulting velocity?
Yes.
All right. All right. So those videos are fine. They're on point. All right. But I'm going to add more videos using that approach or this approach specifically. And then I'll also perhaps upload some PDFs with exercises as well as solutions so that you can measure your solutions against mine.
Hello, sir.
Yes.
In that PDF with solutions that you'll upload, I don't know if it would be possible if you uploaded fully worked solutions so a person can see exactly where they went wrong.
What do you mean fully worked? My solutions are always fully worked.
Sorry?
My solutions are always fully worked. So what do you mean by fully worked? For instance, look here.
Oh, I mean,
These are my solutions.
I thought you meant you're just gonna put a final answer.
No. Solutions. Not just
Okay,
answers.
sir. I understand now.
Yeah.
Sorry, sir.
Uh-huh.
I still have one course there by Moodle, sir.
You still have?
One course there by Moodle. Only have mechanotechnics there by Moodle.
Who's this? Okay. Just send me a message in the group. Send me your student number, surname and initials.
Okay, thank you.
The Meccano one. Is there content on that Meccano one?
No, sir. I also have the same
No, sir.
problem.
Okay, right. So I'll register you guys myself. I guess if you need something to be done right, you have to do it yourself. Yeah. But yeah, I'll register you guys myself. No?
Thank you, sir.
But for now, just send me your student numbers, surname and initials on the engineering science group. All right. I will communicate in the Meccano group when I'm dealing with Meccano. No? So just be ready for when I communicate in the group, the Meccano group, asking for you guys to send me your details.
Yes, sir.
All right. Any more
Hello,
questions?
sir.
Huh?
Will you make this lesson available on the WhatsApp group? This lesson in particular?
Yes, I'll download, then upload the lesson just now on my channel.
Thank you,
Send you
sir.
the link. Yeah. Any more questions? All right. You guys go enjoy your books, and I will enjoy my Friday.
Yeah. ne.
Yeah, it's like that. It's like that.